Welcome back to chemistry, everybody. I hope you guys are doing well so far. I hope we're all staying safe and healthy and home. So we are continuing on with the acids and bases this week. We have been learning about the basically the definitions of what an acid and a base are. We can now look at a chemical and decide if it's an acid, if it's a base, and we can name it. And so now we want to reference this concept of pH. Most of us have heard of pH before, and most of us have not heard of pOH. But like I say, pH, this is something that most of us are familiar with. This idea of a scale that goes from 1 through 14. Or I guess 0, we should say 0. 0 through 14. This is typically an acid, and this is typically a base. And we know that right in the middle at 7, things are neutral. And this scale is based, this scale is based on pH. Well, what is pH and how do we find it? Now, when we're looking at the pH scale, what pH actually stands for, so we recognize this scale. We know that things that are down in this location here, these guys are very acidic, these guys are very basic, and these are essentially neutral. And so when we're doing this, what we're actually doing is when you look at the name pH, the P stands for the power. And the H stands for H+, because remember, in most of our definitions, whether it's the Arrhenius or the Bronsted-Lowry, we know that acids donate H+. And so this explains why acids typically have very small values. So something that's really acidic, when I was younger, this always bothered me. How is something that is so acidic, why does it have such a small number? And why is something that's basic have a really big number? Well, it comes down to what we're actually measuring. We are measuring the H+. And acids have a lot of H+. But how does that give us a small number? Well, remember that it's the power of the H+. And basically what we're looking at are numbers like this. If you have an H+ concentration, so it's basically, we put brackets around this, so it's the molarity of H+. If you have something really big like 1.0 molar, as opposed to something like this, 0.1 molar. Well, if we put these in scientific notation, this is 1.0 times 10 to the 0, right? We don't need to move that decimal. If I put this one in scientific notation, this is going to be 1.0 times 10 to the -1, right? Because we would move that decimal one place to get it into scientific notation. And what we do is when we take the power, what we're doing is we're using logarithms. And logarithms basically are focusing on this piece. They get rid of the 10. So if you take the log of this value right here, the answer is 0. And if you take the log of this value right here, the answer is 1. And so if you have a base, what do bases give us? Bases give us OH-. Are they giving us very much H+? Absolutely not. So we get numbers that look like this, 1.0 times 10 to the -14, right? This is a very, very small amount of H+ in solution. Why isn't there much H+? Because the base is giving us OH-, not H+. So I have very little, and when we negative log it, what do we get for our answer? 14. So basically, we're measuring the size quantity. So the power is basically taking these really, really tiny numbers and just making them more user-friendly. But it's a little misleading there. Okay, now when we're solving this, our equation, our official equation here, is the pH of something, right, is equal to the negative log of H+. Why the negative here? Why the negative sign? Because when we solve this, remember what we had? We had this negative here, and we want to get rid of that negative so that it's a positive number. So it's just basically there to flip the sign for us. So it's the power of hydrogen. We're using a very simple equation. Now, a lot of times people see this log right here and they start freaking out. They're like, no, I hate logarithms. I learned logarithms in math and I still don't understand it. Really, guys, this is as easy as it gets. Okay, you don't really have to understand logarithms much more than where is the button on your calculator that says log. As long as you could punch that button, you're in good situation there. So let's take a look at an example. What is the pH of a 0.15 molar HCl solution? Okay, what is the pH of a 0.15 molar HCl solution? Now, what we want to do is first understand that the acids need to dissolve, okay? They need to give us H+. That's what we're trying to always figure out. We need to say, all right, well, we have some HCl, and it's dissolving to give me H+ and Cl-. We've been writing a lot of dissolving equations back with KSP and KEQ and back when we were learning about like dissolves like with water. So we should be getting used to separating things into their ions. You do not want to write HCl turns into H2 and Cl2. That's a decomposition reaction, not a dissolving process. So make sure that we're getting them into their ions, not their elemental forms. Now, the next thing we need to ask ourselves is how well do these things dissolve? And we know that KSP describes that for us. If it's really big, it dissolves really well. If it's small, it doesn't dissolve well. Well, there are several acids that dissolve really, really, really well. And they dissolve so well that we don't really even calculate the KSP for them. They're just super soluble. And so I'm going to list those off to the sides here. We have HCl, HBr, HI. We have HNO3. We have H2SO4. And we have HClO3. These are what we call strong acids. And they basically will dissolve 100%. When these things hit the water, if I had 100 of these, in the end, I will have 0 of these and 100 here and 100 here. Okay? That's what a strong acid does. Now, if it was weak, you might start with 100 HCl's, and in the end, you might have 80 here, right? And so that would leave us with 20 here and 20 here. Okay, so you're only getting part of it dissolving if it's weak. If it's weak, it basically means it has a smaller KSP value. So what we're looking at here is a strong acid. So if I started with 0.15 of these, when this dissolves, this is going to basically disappear and go to 0, and so I will have 0.15 and 0.15. I know that this is the same because it's a 1 to 1 to 1 ratio. For every one of these, I get one of these. So if I had 0.15 of the HCl's, then I'm going to end up with 0.15 of the H plus and 0.15 of the Cl minus. So now at this point, what I just did is I said, oh, look, I figured out my H plus concentration. So what would my pH be? pH is equal to negative log of 0.15. Okay? And so at this point, you just stick it right into your calculator, just like you see it. You hit the negative sign, then you hit the log button, and then you hit 0.15. This is how most calculators work. So this is how mine works. For example, most of the newer Casios and TIs work. I hit the negative, I hit the log, I hit 0.15, I hit equals, and I get a big long number. And since I have 2 sig figs here, I'm going to put 2 decimals in my answers. So I'm going to go 0.82 is my pH. And there's no specific units that are attached to this. You would just say that the pH is equal to 0.82. Okay. Now, what if we were asked to go backwards? What is the H plus concentration for a solution with a pH of 2.56? So I know that pH is equal to negative log of H plus. And so this is going to be 2.56 is equal to negative log of my H plus. So how do I get the H plus by itself? Now for this, you're going to first move that negative to the other side. So we're dividing by -1, so you get negative 2.56 is equal to log of H plus. And then to get rid of the log, this time you hit shift log on your calculator. So it's basically 10 to the negative 2.56 is equal to H plus. And when we get that in the calculator, we get, so I had 2 decimal places, basically the number of sig figs equals the number of decimals in your pH. I'm not going to be super picky on sig figs here. I'm not around to really focus on this with you guys, so that's kind of a minor detail. If you get the general idea of how to calculate, I'm going to be happy here. But this would be 2.8 times 10 to the negative 3 molar, right? Because I had 2 decimals in my pH, and so that means my original concentration had 2 sig figs, and that's what we're seeing there. So this is my answer. Okay. Now you'll look at this one. This one, we have a 6 molar solution, and I believe this is called formic acid, HCOOH. Is dissolving. We see that H in front. We're going to go ahead and take that one off. So that H is going to come off. COOH with a minus. So I'm breaking it into its ions, right? We take the plus off, and that's going to leave a minus left behind. Now this one, though, you'll notice HCOOH is not on my list of strong acids. This is a weak acid. It does not dissolve 100%. In fact, this one only dissolved 1%. This one only dissolved 1%. Okay. So if this one only dissolves 1%, what would my concentration here be? So now, if it was 100%, this would go to 0, and this would be 6.0, and this would be 6.0. But am I getting 100% turning into an H plus? No, I'm only getting 1%. So 6.0 molar times 1% is equal to what? Now, when you multiply by a percent, remember you got to move that decimal. So this is going to be 0.06. So you'll notice that a weak acid is not going to be giving me as strong or as low or as powerful of a pH. So now this one we would go pH is equal to negative log of 0.06. I guess I could have put another sig fig on there because we had 2 sig figs in the beginning. So when we put this in our calculator, we hit the negative. We hit the negative here, then we hit the log, and then we type in 0.060. And my final answer is 1.22. Right? So you notice the difference here. My concentration was way higher. Right? Look at this, concentration is only 0.15. Look how low my pH was. This concentration is much, much, much higher, but look at my pH, not as low. Why is that? Because this one, even though it's really concentrated, is it actually giving me much in the way of H+? Absolutely not. It's barely dissolving, so it's not going to give me as low of a pH. Okay, so chemicals that we're really familiar with that are like this, vinegar would be a really common one. The acids that we find in soda are very much like this. They are weak acids, and so they don't drop the pH as low. Okay, so we can still have these acids in our bodies and they're not as harmful because the H's just aren't coming off. So this is what we have for acids, but what about bases, right? Now, if we look at something like this, NaOH, they're asking me for the pH. We know that pH is equal to negative log of H+. But we got a slight problem, right? Let's take a really quick look at this chemical right here. Do I see any H pluses in there? If we take this apart, NaOH dissolves to give me Na plus and OH minus. Uh-oh. So if I started with 0.25 of this, we also have strong and weak bases. If you see something from column 1 or 2 with OH minus, it's strong. So let's say, for example, I saw something like this, AlOH3. This is not from column 1 or 2, so this would be weak. Okay? So if it's something like sodium or potassium or barium, these things are from columns 1 and 2, and they tend to be strong. So this one's dissolving really well. So in the end, I'm going to get 0.25 and 0.25. It's going to dissolve 100%. But when I go to plug this in, I have an OH, not an H+. So there's two things that we could do here. There's two ways to solve. This is how most people do it. Instead of using pH, they use POH. POH is equal to negative log of the OH minus. Okay. An alternative is you could use this. KW is equal to the concentration of H plus times the concentration of OH minus, and KW is equal to 1 times 10 to the negative 14. So what you could technically do is take this value and plug it in here for OH, and you can solve for the H+. Because we know that 1 times 10 to the negative 14 goes here. And once you have the H+, you can plug it in up here and then move along. How most of my students, I find, prefer to do this is they like to use this equation right here. Okay, so we're going to plug that in. We're going to go the way that I've seen in the past people prefer to do. So we have negative log of 0.25. And so when we plug this in, we get, what do we get here? 0.60. All right, but this is POH, and that doesn't answer the original question. So what they do is this one last really quick conversion. We know that there's a second equation here, pH plus POH equals 14. Right? So that's a really easy, quick subtraction problem that goes, so the pH is basically equal to 14 minus 0.60, which is 13.40. So you solve it the exact same way. You find whatever's being donated and you negative log it. But when it's a base, you simply have one additional step. You have to subtract it from 14 to get your final answer, to convert the POH into the pH. All right, so we have a couple of equations that we have to watch out for, right? We need to know this one, we need to know this one, and we need to know this one. This equation is also useful, but like I said, I find most students tend to use the other three. but you'll get the exact same answer no matter which way you go with it. All right, talk to you guys soon.